Hello there, welcome to Upper 6 Further Maths. Here we're looking at how to draw graphs with polar coordinates. So we can answer questions from exercise 5b. So we're going to go through some easy ones to start with and then have a look at how you can draw a general graph from the original Cartesian graph. So some easy graphs to get us started. R equals A, where A is just a number. We saw this in the previous video. When R is equal to 5, the radius is always equal to 5. And here when the radius is equal to A, it's just a circle with radius A all the way around the circle. It doesn't matter what the angle is, the radius is always equal to A. So that's a nice straightforward one there. What about theta equals A? Another straightforward one here. Well, let's just imagine for a second that theta equals 3 pi by 4. Then the angle, it's all the coordinates where the angle is equal to 3 pi by 4. We did a similar type of question when we looked at loci in complex numbers. So in this case, it's just a straight line where the angle of measurement round from the x positive axis is A, or 3 pi by 4 in my little example over here. Yes, we did a very similar question to this in loci in complex numbers chapter. It's referred to as a half line. A line would extend off to infinity in both directions. This is a half line. It stops at one point and then will carry on to infinity in one of the directions. Sometimes you draw the dotted bit, but you don't need to. Okay. Another slightly more difficult graph here is R equals some scalar multiple of theta. So R equals theta is the base graph here, really. So in this graph here, the radius is going to be equal to the angle of rotation that you've rotated round on that kind of spiral. So what we need to imagine here is as the angle gets bigger, the radius is also going to get bigger as well. So if we draw out some coordinates here, 0, pi by 2, pi, 3 pi by 2 and 2 pi, the kind of quarter way round points, then the radius is pretty much exactly equal to it, but we need to multiply it by this scale factor A. They like including a scale factor of A in these types of questions you've probably seen before. So what we'll do then is we'll draw ourselves a grid, and this grid will have the x positive axis going to the right, and then just some lines just to refer to the quarter way marks, pi by 2, pi, 3 pi by 2, and back to 2 pi again. Now what's going to happen here is as the angle gets bigger, the radius is going to get bigger. So it starts at 0, 0, then as it rotates around, it's going to get to pi by 2, then as it rotates around again, it's going to get to pi, rotates around again, it's going to get to 3 pi by 2, rotates around again, it's going to get to 2 pi. So it's going to start at 0, and then as the angle increases, the radius will increase as well. And it's quite an interesting little spirally curve here that we're going to get. So as the angle moves round, the radius is going to move round as well. So as we rotate around, the angle, so as we increase the angle, we increase the radius as well. Bigger angle equals bigger distance. Lovely. And in some cases, it's actually easier to rearrange the formula before we start drawing the diagram. And in R equals A sec theta, this is the easier way to go. So rearrange the formula, times both sides by cos, and then realize that R cos theta, or recognize that R cos theta equals x. So replace x here where you've got R cos theta. So x equals A. So it's just the simple graph where all the x coordinates are equal to A. So sometimes it's easier to rearrange the formula. But we're now going to have a look at how you might convert a normal Cartesian graph into a polar graph. So we're going to draw here R equals cos theta. One thing you could do is you could draw a table of values, but really I'm going to want to show you how you convert the Cartesian graph to the polar graph. So once we've got that, we've got the graph. And now we're going to transform it onto a polar graph. So what I'll do here, so the reason I've drawn this graph here is that it's helpful to visualize that the y-axis here is effectively the r value. So it's effectively the radius of the distance from the center point as the angle rotates round. Notice here I'm going to have some negative radius values, and we'll see what happens there later. and the x-axis is the angle of rotation around the graph. So as we rotate around the graph, we'll be moving on the x-axis, and that will it will give us a coordinate relating to the height or the depth of the y-axis or the radius. So let's just move some bits out of the way then. Let's budge this stuff up and then get out some polar coordinate graph paper. So let's have a look then at this first section here that's now been highlighted in green on the Cartesian grid. What we'll have here is we'll be dealing with these 4 coordinates here. Now we can see here the first starting coordinate will be the coordinate of angle 0, radius 1. So the first coordinate we're going to plot has appeared here, small x symbol. As the angle is 0, the radius is 1. As we now move around the circle to pi by 6, the radius is going to slightly decrease to root 3 over 2. So that's where this next coordinate appears from. As we move round the circle again, as we increase the angle around the polar coordinate graph, we are going to be reducing the radius to a half. You can see here the radius is decreasing on this green section of the graph, and you can see it's decreasing on the numbers here as well. So the next coordinate will be pi by 3 round and then a half out from the coordinate 0, 0. Once we've moved round to 90 degrees or pi by 2 radians, the radius will be 0. So that's why we're going to have to now intersect the origin. And we can see here on the graph, at pi by 2, we need to intersect the origin. So this part here is going to form a nice little circle as we move round from the starting coordinate and go through the 3 other coordinates that we've plotted. Let's now move on to the next section of the graph. Then the next section of the graph is in between pi by 2 to pi. So you'd expect the next section of the graph to appear up here, in between 90 degrees to 180 degrees. And the values we're going to use here they are negative. Now that's going to affect our graph. We're going to have a negative radius here where we'd expect the graph to appear in this section here. We'd expect the graph to appear in this section here because it's in between the angle of pi by 2 and pi. But they're not going to appear in this top left-hand section up here. They're actually going to appear in this bottom right-hand section. What's effectively going to happen here is because these radius values are negative, they're going to be reflected through the origin onto the other side. They're effectively going to be multiplied by a scale factor -1 through the origin. So let's see what happens. The first coordinate here, if it was positive, would be up here. It would be at 0.5 radius with an angle of 2 pi by 3. But because it's actually going to have a radius -half, you can tell this on the graph because it's below the x-axis on the graph, on the negative portion of the graph, it actually gets reflected through the coordinate 0, 0 by a scale factor -1 effectively. Let's move on to the next coordinate. If this was positive root 3 over 2, it would appear over here on the angle of 5 pi by 6. But actually it's negative root 3 over 2, so I'm going to reflect it through the origin to this coordinate here. And the same will happen with this pi -1, angle of rotation pi, radius of 1, but it's not 1, it's -1, so it needs reflecting through the origin. So you'd expect the coordinates to appear up here, but actually they all get reflected through the graph to this bottom right-hand section. Let's carry on the graph, and we're now moving on to the next section of the graph, which is in between pi to 3 pi by 2 in this bottom left-hand section here. But we can see here we've still got some negative values. You can see that on the graph here. It's on the negative portion of the graph. So you'd expect it to appear in the bottom left here, but because the radius is negative, it will actually appear up here. So let's think about it. If the gradient, let's start with this coordinate here, 7 pi by 6 minus root 3 over 2. If this value was positive, it would appear on an angle of 7 pi by 6 at a radius of root 3 over 2. But that's actually negative root 3 over 2 on that graph, so it's actually going to appear over here. Same will happen with the half at the angle of 4 pi by 3. It's a negative half, and it will be reflected through the point 0, 0 to the top right hand side of the graph. And it will actually now go ahead and repeat the same graph that we've just drawn before. So it's gone over the line that we've previously used. The next coordinate, 3 pi by 2, was 0, so it went over like that. So it's actually going to start repeating itself. Let's move on to the final quarter of the graph. The final quarter of the graph will include these 4 coordinates up here. Positive coordinates, so positive radius, and we can see that on the graph because we've got a positive output on the radius here. So we'd expect the angle between 3 pi by 2 to 2 pi to appear in the bottom right. That's where the angles are, and it will appear in the bottom right because it's a positive radius. And let's just plot the coordinates. They're appearing slightly in green. You might be able to see them, but you'll definitely be able to see this blue line that's come through the graph just to represent that it's gone over the red line again. So actually this graph here has been drawn twice, once over and then once over again. So that's how you can convert a graph into a polar graph, a Cartesian graph into a polar graph. Think of the y-axis as the measurement of the radius as you move around the x-axis on your graph. We're now going to have a go at r equals cos 2 theta using exactly the same strategy as before. The strategy is to draw the Cartesian graph and think of the output, the y-axis, as the radius, and think of the x-axis as the amount of rotation as we move round that circle. So let's get the graph paper out, and we're going to start first of all at 1. So starting at the coordinate 1. And what's actually going to be helpful here is if we put a dotted line at the angle at which we have it intersecting 0. So actually, if I was drawing this graph without doing it in a tutorial, I would actually go through and identify all of the points at which it was 0 and draw some dotted lines at those points. So we're going to have the graph starting up at 1 at the angle of 0, and it's going to move round the graph to pi by 4, 45 degrees, and the radius is going to be slowly increasing, so decreasing, until it hits the origin, until the radius is 0. Let's move on to the next section of the graph. The next section of the graph will be this next section here, between 45 and 90 degrees, pi by 4 to pi by 2. I would expect it to appear in the second eighth of the graph up here, but because the radius is negative, we can tell the radius needs to be negative because it's on the bottom section of this graph here. It's actually going to appear reflecting it through the origin by a scale factor -1. So what's going to happen here is the graph would have usually have gone starting at 45 degrees to 90 degrees. That will actually refer to starting at near this dotted line to moving away from the dotted line to the 90-degree line. So what's going to happen here, it's going to loop round. It's going to have a very small radius to start with, and then as it moves round to the 90-degree line, or in fact that's going to be reflected down to this point here, the radius moves out to the value -1. Let's move on to the next section. The next section is in between pi by 2 to 3 pi by 4. That would usually be in this top third of the graph up here, but because it's a negative radius, it will actually be appearing down here. It will start with a radius of -1 and then move to a radius of 0. So we'd expect it to start up at 1, and then as it moves closer to this pi angle, it will move down to 0. But that will be reflected on this quadrant here. So it will look like this. The next section of the graph will be the fourth eighth of this graph up here. So you would expect it to appear up here because it has a positive radius. And in this case, the radius starts at 0 because the graph starts at 0, and then it will move out towards the number 1 because the radius will be 1 when it is at 180 degrees, or pi radians. you can kind of start to see the shape that's going to form here. In the next eighth, the fifth eighth of the graph, it's going to have a positive radius, so you'd expect the graph to appear in the fifth eighth portion of the graph, starting with radius 1, and then as it moves around the circle, moves around the diagram, the radius will move down to 0. In the next eighth, the sixth eighth of the graph, you'd expect it to appear in the sixth eighth of the graph section. But because it's got a negative radius, you can tell that because it's negative on this part of the graph here, it will actually appear up here. It's going to start with a radius of 0 and move out to a radius of 1. So it's going to move out to a radius of 1 like that. On the next section of the graph, between 3 pi by 2 to 3 pi, so 7 pi by 4, you would expect it to appear in the 7th eighth of the graph down here. But it's not going to happen, it's going to be reflected through because it's a negative on the radius value. And again, it's going to start with a radius of 1 and move to a radius of 0. So it's going to start up at 1 and then move round to it's having a radius value of 0. And on the eighth section of the graph, it's going to be in between 7 pi by 4 to 2 pi positively. So you'd expect it to appear in the eighth of the graph, and it will move from a radius of 0 to a radius of 1. And there we are, that's the answer to drawing this graph here. R equals cos 2 theta looks like this graph here. Let's just do an action replay of how that graph was drawn. I'll simultaneously be colouring in this graph up the top here whilst drawing the sketch down here. So have a watch of this. Lovely, there we are. So as it's gone over all of the angles, sometimes it's had to be reflected, sometimes it's not been reflected, but it's actually formed a nice continuous loop around the graph. Let's just see it again. So actually you can draw this graph with a continuous loop of your pen around the graph. You don't have to stop at one point, then jump onto the next petal, then jump onto the next petal, then jump onto the next petal, then move on to the final portion of the first petal. You actually doing a continuous flow around the diagram. Alright then, I'm going to quickly go through r equals cos 3 theta, and what you can tell first of all is that I've drawn some dotted lines on my graph. I've drawn dotted lines on the graph at every intersection point with 0 on this original graph. This is the cos 3x graph at the top, and any time it's intersected 0, I've put some asymptotes here because I know the graph will be coming into the origin at those points. So the first point here is going to be at 1, 0, and it's going to move to the origin because the radius is decreasing as it moves round to pi by 6. So the first portion of the graph will look like that. The next portion of the graph you'd expect to appear up in this top right-hand section here, but it's a negative, so we're actually going to have a petal in the bottom left of the graph. As we continue to move round, we'd now be in this section of the graph here, and in fact we will be in this section of the graph here because it's a positive radius. So this will form another petal in this section of the graph, like that. Radius going out, and then radius coming back in. The next section of the graph we'd expect to appear in this section of the graph over here, but because it's a negative radius, it will actually appear in the reflected portion of the graph over here. So we'd expect to see another petal loop going through from this point here to this point here. So let's see that in action, and then it will go back over itself again. So actually we're not going to see petals in all of the quadrants here, or in all of the hexants here, maybe that's the word for it, in 6 different sections. We're actually going to only see petals appear just in every other section of the graph. So from the next section here, it was 7 pi by 6 to 3 pi by 2, so this section here. And in fact, the graph did appear in this section here, if you saw it in blue, because it has a positive radius. The next part you'd expect to appear down here between 3 pi by 2 and 11 pi by 6, but it's got a negative radius, so it's actually going to appear in the reflected part through the origin in the top left. And the final section of the graph is in the right hand side portion here, in between 11 pi by 6 to 2 pi, so that's going to complete all three of the petals that have been traced over twice. Okay, so let's try and see if we can spot a pattern here between these types of graphs. In the cos theta graph, we just had one circle that went over itself twice. In the cos 2 theta graph, we had all four petals. In the cos 3 theta graph, we had 3 petals where it went over itself twice, and we have some sections that are missing from the graph here. When it's cos 4 theta, we have, in fact, 8 petals with no sections missing. And in fact, what I've done here on some graph plotting software is I have plotted the next 4 in this little sequence. So the cos 5 theta has 5 petals with every other section missing, probably because in every other section it's repeated itself over the other petal. Cos 6 theta has 12 petals, cos 7 theta has 7 petals, each repeated twice, and cos 8 theta has 16 petals. So here's this little pattern here, quite an interesting little pattern. Probably don't need to know it for the exam, but I thought I would show it to you anyway. Something very similar would happen if you replace all of these with sine, and in fact that's what I want you to do. If you do have the opportunity, go to the website desmos.com, you don't need to type in the / calculator, and these are the settings that I like to have switched on when I'm on Desmos. So I like to have polar coordinate graphs option switched on, I like to have projector mode on because it's a bit clearer then, and I like to zoom in to about this kind of axis here. What I'd like you to do with all of these graphs here from before, replace cos with sine, and you can see the pattern for yourself. In fact, you could just experiment with all sorts of different polar coordinate graphs on this graph plotting software if you wish to do so. I'm just going to show you a few more of what you would do in an exam if you were faced with, for example, the graph r equals 1 plus cos theta. So as from before, you draw the Cartesian graph. This is the cos theta graph moved up by 1, so it's 1 plus cos theta, and then you draw the graph as if you were drawing a graph measuring the radius as you move round the circle. So for the first section, we might want to draw some coordinates on first. So 2a on the first one, 1a on the second one. This would be down to 0, the radius of 0 here. 3 pi by 2 will be on the line 3 at 1, and then finally finishing it off will be back at A. So the first section will be a loop round from 2A to A in between 0 to pi by 2. In the next loop it will be in between a radius of 1 to 0 in between this quadrant here, so actually it will come in on itself. In the third quadrant, it will go from pi to 3 pi by 2, so in this section here, and it will come out from a radius of 0 to a radius of 1. And then in the next section, it will go from a radius of 1 to a radius of 2, and it will effectively form the same kind of shape as it did on the top. And this shape here is called a cardioid type shape. So 1 plus cos theta is a cardioid shape. And if you just rotate your neck to the right a little bit, you'll probably see a nice little love heart shape. Lovely. What about the graph then? R squared equals A squared cos 2 theta. Now I don't really want you to be worrying too much about the A's that are appearing at the front of this graph. That will just magnify the radius by a scale factor A. It's the shape of the graph that is interesting here. So I'm only really interested in drawing the cos 2x graph. So this is the value of the radius. But if we think about it, this is equal to the radius squared. And you can never have a negative squared value, or a negative value that has previously been squared. So because r squared is always positive, we won't be drawing any part of the graph that is negative or would have a negative radius. So in fact, I'm just going to scribble out anything that would appear on the bottom there. So in fact there will be some gaps in my graph. There will be a gap between pi by 4 to 3 pi by 4 and a gap between 5 pi by 4 to 7 pi by 4. And I'll just be drawing these sections of the graph on my final graph. So I'll plot some coordinates just to get the ball rolling, and in between 0 to pi by 4 the radius will be going down to 0. Then there'll be no graph on this top section here. Then the next section it will start up again is at 3 pi by 4 to 5 pi by 4. There'll be a loop here. Then there'll be no graph in between 5 pi by 4 to 7 pi by 4. Then the graph will carry back on in between 5 pi by 4 to 2 pi, so 7 pi by 4 to 2 pi, which will continue the loop back round to this section here. The loops will be very similar to the cos 2 theta graph, just nothing on the top and nothing on the bottom. Let's draw another graph then. So sketch the graph this time of 5 plus 2 cos theta. Again, you draw yourself the graph. The maximum radius here will be 7 and the minimum radius here will be 3 because cos goes in between 1 to -1, magnify it by 2 and it will go from a maximum of 2 down to a minimum of 2 from the starting point of 5. So in this graph here we're going to start with the radius at 7. Then as we move round the graph to pi by 2 the radius will be 5. Then as we move round the graph to pi the radius will be 3. Then as we move round the graph to 3 pi by 2, the radius will be 5. And as we move round the graph to finish, the radius will finish back on 7. So it's a good idea to draw some points that you will be going through. And the graph will look like this kind of shape here. It's not quite a circle, more like an egg shape. And what you'll see here is that as the angle moves round, the radius is slowly getting smaller and smaller, still getting smaller and smaller until it reaches pi, and then from when it reaches pi onwards the radius will be carrying on getting bigger and bigger until it gets back to the 2 pi angle again. Okay, so there we are. This is more like an egg shape and not an exact circle. Let's just change that 5 now to a 3. So changing it ever so slightly. Again, the graph will go from 5 to 1. But in this graph here, doing exactly the same stuff as we did last time, in fact, what will actually happen here is you'll see a dimple come in and then a dimple, and then the graph carrying on back outwards. In the last graph, in the last video in this chapter, we're going to look at when does it have a dimple and when does it not have a dimple. But you just need to be aware that some graphs have dimples, some graphs are just egg shapes. This graph has a dimple in it. Okay, so that's all we're going to go through in this video then. I picked one question out of the textbook for you to now have a go, and I'll show you how to do it afterwards. So pause the video and give this question a go. Okay, so in this question here, the first thing I'm going to do is draw the graph of 6 plus sine theta. Now for the 6 plus sine theta graph, I've done a bunch of cos examples in the video so far. The sine graph starts at 0. So it will start at 6 because I've moved everything up 6. Then as I move round the graph, it will go up to 7. Then it will move down to 5. Then it will move up back to 6 again. So this is as I go through pi by 2, pi will be here, 3 pi by 2 will be here, and 2 pi will be here. So the way that I draw polar graphs is I just draw the initial line and that's it. So then I'll know that my starting graph will start at 6. It will then move out to a radius of 7, so I've got to draw that a little bit further away than 6. Then it will come back into a radius of 6 at pi radians. And then it will move down to a radius of 5 down here. And it will move back out to a radius of 6 as I move round the circle. So it's going to look like this kind of shape here, where it looks more like an egg shape and not a one with a dimple in, I don't think. You'll know exactly by the end of this chapter whether it will have a dimple or not, but this is the rough shape of this graph here. So there we are. It's a case of drawing the Cartesian graph and then transferring all of that knowledge from the Cartesian graph onto a polar graph where the y-axis measures the radius, and as you go round the circle on your x-axis here. Lovely, quite a difficult chapter, quite a difficult section, that one. Hopefully you found it okay, and maybe you have taken some pointers from it, but it's ultimately going to be when you knuckle down and have a go at some questions that you'll really form your own understanding of how these graphs are drawn. So make sure you have plenty of practice on exercise 5b, and thanks very much for watching.